Okay, the final lesson for the first unit, we're looking at the applications for dot and cross product. So this is some of the side uses that you come across. So today's goal, I can determine when to use dot and cross product, and I need to apply and understand how they be used in a variety of real world applications. So some of these applications are embedded in some of the software you use. For example, anyone that's in drafting has used SketchUp. Vectors and dot and cross product are used in that, and so on and so forth. So the dot product and cross product have a variety of applications. Some of them are practical for us. Some of them are, hey, this is where it can be used, and we're kind of a dead end with some of the problems. But some of them will be carried forward. So the first one, which is very important, and this is something that will go on to Unit 2, so we can't get rid of this one, determining 3-space. So what is 3-space? 3-space is when we have a vector that comes off one of our planes. All right, and the way we had it drawn before. So if we have a vector that exists only on one plane, so if it's on that XY plane, okay, that's 2-space. What we needed to do is to move off into the Z direction to get 3-space. So 3-space means that it moves off the plane. So with 3-space, when we want to determine do 3 vectors represent 3-space, let's think of a piece of paper here for a second. So here's my piece of paper. If all 3 vectors are on the same plane, so U, V, and W, they're what we call coplanars. They're all on the same piece of paper. If I was to take U cross V, my result of U cross V would be a new vector that is perpendicular to the page, because when you take the cross product of 2 vectors, you end up with a brand new vector that is perpendicular to the page. All right, so I'll say perpendicular to plane. Now, the third vector, the one that we're interested in, the W vector, we want to know in 3-space, are all 3 vectors on the same piece of paper? Because if all 3 vectors, U, V, and W, are on the same piece of paper, it's what we call 2-space. Because if you're on this piece of paper, and I asked you to leave this piece of paper by using vectors U, V, and W, so say they're directions you're being pushed, U is only going to push you on the piece of paper, V is pushing you around the piece of paper, W is pushing you around the piece of paper. We're looking for that vector that pushes you off the piece of paper. So that's what we're really looking for here. So is W that vector that gets you off the page, or is it the vector that's on that page? Well, if we were to take our results of U cross V, so that's the green vector I've drawn there, one perpendicular to the page, and I did the dot product of W, we have 2 possible outcomes here. And our 2 possible outcomes would be equal to 0 and not equal to 0. If it's equal to 0, then we know the vectors are perpendicular. So what does that mean? Just coming down there. If U cross V and W are perpendicular, then U, V, and W are coplanar. Coplanar, which means not a basis for space. Not a basis for space. So that means that if U, V, and W represented, pushes or thrusts for you, you're being pushed around this piece of paper. W will not lift you up and off the piece of paper, so it's just being pushed. You're being pushed horizontally around. If it's not equal to 0, then it would not be perpendicular. So not perpendicular. Therefore, a basis of space. So that's basically the question. When you're talking about 3 vectors and are they 3-space, it's basically asking, is W on the piece of paper, or is W pushing u off the piece of paper. So that's our quick test right there. So therefore, here's your three-space test, and we'll need this in the next unit. And we're talking about coplanar vectors. You take any of the two vectors and do the cross product. So u cross v, for example, dot it with w. And I'll leave it as a question mark, and you can put the two cases in. So that will help you determine whether three vectors constitute space or not. So looking at the example here, determine if the given vectors are a basis for space. First thing I'm going to do u cross v, which will result in a vector. So 2, negative 3, 5, 2, negative 3, 5, negative 1, 0, 3, negative 1, 0, 3. Crossing off my ends. I'm going to speed up the process here. So I have negative 9 minus 5, so we have negative 14. The next one, I would have negative 5 minus 6, that's negative 11. And the last one, 0, take away 3, so negative 3. So there's u cross v. So now, u cross v dot with the third vector. So I have negative 14, negative 11, negative 3, dot with negative 4, 1, 0. So now you're saying to yourself, well, I'm going to need a calculator for this. No, you don't need a calculator for this. You know it's going to be a positive number. Remember, it's a scalar now. When you do a dot product, our result here is going to be scalar. It's going to be a number. So when you do 4 times 14, that's really 2 times 14 is 28. And you double that, and you get positive 56, minus 11, and then plus 0. All you need to know is it's not going to be 0. 56 minus 11, it gives you 45. It doesn't matter. It's not equal to 0. So therefore, u, v, and w are a basis for space. Okay, if it was equal to 0, then the resulting three vectors would be coplanar on the same plane. All right, so there's the first part. All right, the next component is dealing with projections. So what we're talking about, before we were projecting the xy, or a vector onto an xy axis, so we draw the xy axis, and we are getting that shadow, putting that component, finding the x component for the vector. What I want to do now is I want to put that x component on any vector, regardless of the orientation. So I want to take vector u, and I want to project it onto v. So I want to find the shadow of the projection of u. So we're basically going to find how big is the shadow. So magnitude of shadow, because it's going to be in the direction of v, because we're putting it onto that vector. So we're basically shining a light above it, and we're going to find that shadow. So how do we do that? Well, the angle between two vectors, u and v, is given by theta. So we know that the projection, and it's the notation I'm not a big fan of, but we work with what we got. Just a sec, my pen's out of control. There we go. U onto v equals, so there's the notation, projection u onto v. Well, we know that the component, if we treat the v vector like an x-axis, so if we say, well, let's just pretend this is the x-axis, then how would you find that shadow? Well, we would say, well, it's the projection of u, or the vector u, magnitude of u, sorry, cos theta. All right, and to give it a direction, because this is going to be a vector, this projection is still going to be a vector. So right now, all we have is a magnitude. So I'll just do that above. So that's a magnitude. What's the direction of this magnitude? Well, it's in the direction of the v vector. Okay, so there is the direction So now we have the early part of the formula. Now to clean this up or to make it more simple, it would be nice if we can get rid of this cos theta and just deal with the vectors themselves. So this formula looks very, very similar. You start to see the basis of our dot product, right? So what we can do, or what mathematicians have done, they've said, okay, let's multiply the top by v, cos theta, multiplied by the v vector. But to keep the equation balanced, I also have to divide by v. So those two really cancel each other out. So we're multiplying the top and bottom by the magnitude of v. Because what that does, we can now replace magnitude of v cos theta with the dot product. So we end up with, in brackets, u dot v, which is a scalar. Magnitude of v gives it direction. And what the denominator essentially does is makes it into a unit vector, makes v into a unit vector. And just showing that one extra step. So really you end up with u dot v multiplied by the unit vector of v, if you think of it that way. So basically what we're doing, vector v gives it the direction, and by making it a unit vector, oops, there we go. Okay, and I'll leave it at that. So those are the two formulas, and it really, this is the one that the textbook prefers, and it's the one I tend to use most often. But I just wanted to show or make sure you see that all you're doing is you're finding a unit vector v, and you remember unit vector is a magnitude of 1, gives you a direction, and then you're multiplying the shadow length by 1, so now you have the right length of shadow. So there we go. So there is our formula for the projection of u onto v. Sorry, I made a very, very small mistake, and it goes back to this first part. I just realized now, this direction, that v vector, it should have already been in a unit vector form, so we should have had it divided by the magnitude of v, because that's the direction. It's when it's providing us a direction, we want it to be a unit vector. So what does that mean? It doesn't really change anything, except for now there was already a v in the magnitude of v in the denominator, so that should be squared, that should be squared, and that should be squared. So it's been a circular argument. So this last line, it's correct, but like I said, you really want the one that's boxed in red. So magnitude, if you're just looking for the magnitude of projection, then the formula for that and the notation, really, they don't really have it equal to anything, magnitude of projection. So I just leave it as magnitude projection, and that's fine notation to leave it in. It is the absolute value of u dot v, because it's a measurement of distance divided by magnitude of v. So that will get you just the length of the shadow. So length of projection, or magnitude only. And this has magnitude plus direction. All right, so there's your projections. I'm going to show you a couple of examples of how we use them in today's applications, and then again, this projection is going to come back and we need it in Unit 2. So again, very important knowing how to do it properly. If you have any questions, make sure you find me, and we'll finish up this lesson in the next video.